All right, so let's talk about quantum theory today. So last time we said that Rutherford's experiment led to the development of what we now know as the nuclear model of the atom. That gives us a correct picture, as far as we know, of based on experimental data of what an atom looks like. Okay, it's got a tiny nucleus in the middle with electrons roaming around it. The problem with that, though, people had problems with that right away because at that time, they know that such a thing could not possibly be stable. You cannot have a negatively charged electron, negatively charged particle going around a positively charged particle and have that thing stable. Okay? But there it is. The experimental facts from Rutherford's experiment says that that is what the atom is. That's what the experiment suggests. Okay, so the that is still the currently accepted model of the atom, but we need to be able to explain it. And so what they knew with physics at that time, what they knew in physics at that time, the kind of physics that gets taught to you in your introductory physics classes cannot explain that. Okay, and there were also several other anomalous, you might say, anomalous experiments at that time that also could not be explained by the kind of physics that you get taught in your introductory physics classes. Okay, so that led to the development, all of the problem with the nuclear model uh, and these anomalous experiments that could not be explained by the physics that's known at the time led to the development of what we now know as modern physics. Okay, so the physics at the time, the kind of physics you get taught in your introductory class, like introductory physics courses, is now known as classical physics. So, and as something becomes classic, that simply means it's old physics. Okay, so like when they came up with the new formula for Coke in the 1980s, the old Coke, the original formula became known as Coca-Cola Classic. So anyway, the failure of classical physics to explain the nuclear model of the atom, as well as other phenomena that led to the world, that led to the development of modern physics. Okay, primarily had to do, a lot of these anomalous experiments primarily had to do with experiments that dealt with light. Okay, light was involved in all of these. So anytime you're dealing with phenomena in the world of the very fast, okay, so things that are approaching the speed of light, okay, you're going to need a better theory than classical physics, and so out of that came the theory of relativity. Now, the failure to explain phenomena dealing with the world of the very small led to the development of what is known as quantum mechanics. Okay, so those are the two major branches, you might say, of modern physics that arose towards the end of the, what would that be, 19th century. Okay, so late 1800s, early 1900s. That's when quantum mechanics and relativity were developed. So those are the two major branches of physics. And we're going to focus today on quantum mechanics, quantum theory. Okay, and that's because that is what's more useful to us because we're basically dealing with the world of the very small, the world of the electrons. Okay, barely hear me today? I'm sorry. Let me adjust my audio. Okay, let me just pause the recording for now. All right. Okay, so you're gonna get to see this video on YouTube anyway. So whatever part you missed because of the audio problem earlier, you can just go through the YouTube video later. But just to recap what I've just said, the idea was that the main ideas I covered so far was that towards the end of the, that would be the 19th century, so that's late 1800s, towards the turn of that century, towards the 1900s, okay, there were several anomalous phenomena that they could not explain by the kind of physics that they teach you in introductory physics classes, like Newton's laws and all that. And so that physics that was known at the time, which is still being taught as which is what's taught in your introductory physics courses, is now known as classical physics. So a modern physics had to be invented. So there's two major branches of modern physics, relativity and quantum mechanics, that would allow us to explain this anomalous phenomena. And among these anomalous phenomena, most of these had to do with light. And this would also allow us to explain the nuclear model of the atom, okay? Because everything they knew at that time suggests that the idea of a charged particle, like an electron, going around a positively charged particle, like the proton, would lead to something very unstable. The atom as we know it, if the physics at that time was correct, the atom as you know it could not possibly exist, because it's not going to take very long for that electron to crash into the nucleus. So we should not even be observing an atom that follows the nuclear model. Okay? So, like I said, we're going to focus on quantum theory in this lesson, because that's what's important, that's what's most useful to us in chemistry, since we're dealing with the world of the very small. We want to be able to understand the electron, chemical properties, substances, the properties of atoms primarily depend on the behavior of the electrons. Okay, so let's talk a little bit about light. Okay, like I said, experiments dealing with light were critical to the development of modern atomic theory, and this is the part of the theory where we talk about the behavior of the electrons within the atom. And so we need for us to be able to explain or understand the behavior of the electrons, we need quantum mechanics. Okay, we cannot use Newton's laws for that. So light is also known as electromagnetic radiation. So let's first try to understand why light is called an electromagnetic radiation. Okay, first of all, prior to the development of quantum mechanics, it was pretty much accepted that light is an electromagnetic wave. So let's try to understand what this term means. What's a wave? A wave is a periodic disturbance that's propagating through space. So it's something that repeats itself, a disturbance that repeats itself over and over and over again as it moves through space. So periodic means repeating. Okay, electromagnetic. Okay, so that adjective right there that you put in front of the word wave simply means that you're dealing with a disturbance that affects charged particles. Okay, so electromagnetic forces are forces that are associated with charged particles. And what this disturbance basically does, it transmits energy from one point in space to another. So it's a way for energy to move from one point in space to another. Let me just give you a simple analogy that would drive home this concept of transmitting a wave as a way of transmitting energy. Imagine you were to drop a rock on a pond. Okay, so what happens when you do that? As it hits the water, it's going to generate water waves, right? So imagine now you have this cork a few meters away from where you dropped the rock. What happens as the wave passes through that cork? That cork's going to bob up and down, right? So what you're doing there is, by generating that water wave from the rock, you're transmitting the kinetic energy of the rock to the cork. Okay, so the rock has kinetic energy as it hits the water wave propagates. Okay, so it transmits the energy away from where you dropped it, and now your cork ends up gaining kinetic energy. All right, so it's an electromagnetic wave. And exactly what is it that's waving in an electromagnetic wave? Like I said, it's called electric and magnetic fields. Electric field is just the force that a charge of 1 coulomb would feel at a given location. Okay, so you can see here's a plot of the electric field versus distance. So this is distance right here. Okay, so this plot right here, you can see it's going through cycles. That's one cycle, that's another cycle, that's another cycle, that's another cycle. All right, so it's repeating. That disturbance is repeating. The magnitude of the electric field, okay, the actual value of the magnetic field, let's say at this point it would be that. At this point the electric field is 0. At this point the electric field would be this one. The value of the electric field tells you the magnitude of the force that a charge of 1 coulomb would feel at that particular location. Okay, Now you can see it can be positive or negative. It simply means if it's positive, then a positively charged particle will feel a force going that way, right? Uh, and then if it's negative, the force would be directed in the opposite direction. Like here, the force is negative, so the force that the particle would be feeling would be towards the opposite direction. Okay? So the force that the particle would feel is strongest at the crests and the troughs of the wave. So the crest is where you get this highest value right here. This is a crest. This location is a crest. This location is a crest. So at these locations, your particle is going to experience the strongest force from the wave. And also at the trough. So this location down here is a trough. Okay. And this is a trough. And that's a trough. Okay, at that location, your particle is going to experience the strongest force. Okay, and there are places where the particle will not feel force, and that would be at the node right here where the electric field is 0. That's a node, that's a node, that's a node. Okay, so here, this line right here, this blue line is where the electric field strength is 0. Now, the magnetic field is another wave that oscillates perpendicular to the electric field. Let me show you a better picture than what I can draw here from one of these websites that I linked to in the free Moodle course site. So this thing right here from Hyperphysics from Georgia State University. So this website is hyperphysics.phy-astr.gsu.edu, and I have that pulled up already for you. Here's a better picture of an electromagnetic wave. Okay. So the red arrows right here, okay, the length of these red arrows right here tell you the strength of the electric field at the different locations. So you have a wave here that's moving in that direction, okay. So the red, you can if you call this your z-axis and this is your x-axis and that's your y-axis, okay. Then you say that your electric field here is oscillating in the xz plane, okay, up and down, and then your magnetic field is oscillating on the xy plane. So it would be oscillating on, if you imagine your xy plane as a table, okay, your magnetic field is oscillating on the table, and then okay, let's see. So this was. So your xy plane would be the plane of the table. So you would say your magnetic field is oscillating that way, and your electric field will be oscillating this way. Okay, so that's your oscillation right there of your electric field. Here's another picture of it. Okay, this one's an animation. This is for you to realize that this electric field and magnetic field wave is actually moving. So this is, you can see the oscillation. So within a particular location, the electric field actually oscillates. So here it's getting weaker. It's getting, okay, so if you keep track of this one right here, it's getting weaker, and then it goes to 0, and then the electric field vector goes negative. Okay, just follow the arrow that I have, and then it goes weaker again, and then it goes back up and down. So at any given location, it oscillates up and down. Same thing with the magnetic field. Okay. So that's an electric field, electric field wave propagating through space. Okay. All right. So what are the things that we can use to describe an electromagnetic wave? The speed of the propagation of the magnetic field wave, electromagnetic wave is 2.998 times 10 to the 8 meters per second. So that's about, what, 299, that's about 3 point, you can round that up to 3 sig figs, that's 3.00 times 10 to the 8 meters per second. So that would be 3 with 8 zeros after that, right? So that's 300 million meters per second, or 300,000 kilometers per second. That's how fast that electromagnetic wave, that's how fast light moves, okay? So that's the speed of the wave, and that's in a vacuum, okay, and it's not that much different through other materials. The distance between consecutive crests and troughs is called the wavelength. Okay, the length of the cycle is called the wavelength, and it's given by the Greek we usually symbolize it by the Greek letter lambda. And the frequency of the wave, okay, that corresponds to the number of cycles that pass through a point every second. So let's say we pick a point right here, okay? Okay, if we were to just focus on this location right here, how many cycles would pass through this point? Remember, this is a traveling wave every second. If you did that, then you get what's called the frequency of the wave, okay? Now, since the distance traveled, okay, the distance traveled every cycle is lambda, and the number of cycles that pass a point at any given per second is given by frequency. Lambda times frequency would be equal to the speed of light. Okay, and a way to think about that is to say that, okay, look at your units right here. Lambda is in meters, and frequency is per second. So meters per second. That will give you the speed of the light, and that speed of the light was previously measured to be close to 3 times 10 to the 8 meters per second, but now, okay, in the modern definition, it is now defined to be an exact number. I gave you that exact number earlier in the semester, and that's now being used to define what a meter is. It used to be that they defined how long a meter was, okay, and then they figured out that the speed of light was 3 times 10 to the 8 meters per second. Nowadays, with the modern definitions, they fix the speed of light to an exact number, and this is not the exact number. There's a few more decimal places after this one. And then based on that, they have redefined what a meter, how long a meter is, okay? So that's frequency and wavelength, all right? So let's do a little calculation right here. What's the frequency of green light that has a wavelength of 500 nanometers? If you were to see green light, light that has a wavelength of 500 nanometers, your eyes are going to perceive it as a green light. And let's see if we can calculate what the frequency is. What was the relationship? Lambda times frequency is equal to the speed of light. So if we want to solve for frequency, what do we do? Frequency is new, so you divide both sides by lambda. Okay, and that gets rid of lambda from the left-hand side, and so you can say your frequency is equal to c over lambda. So you put in speed of light is 2.998 times 10 to the 8 meters per second, divided by our wavelength, 500 nanometers. Nanometers means 10 to the negative 9, so that's 500.0 times 10 to the negative 9 meters. That's your wavelength. Okay, so let's put 500.0 times 10 to the negative 9 meters. And what would that be? Let's plug that into our calculator. 2.998 times 10 to the 8 divided by 500 times 10 to the negative 9. Okay, and that gives us 5996. And how many zeros after that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 14 zeros after the 5. Okay, so 5.996 I have times 10 to the 14. Meters. It should just be per second. Okay, so that's the frequency of the wave, or 6 times 10 to the 14. If I think I may have done this calculation before with just 3 times 10 to the 8. So it's 6 times 10 to the 14. That's close enough to 6. Okay. Per second is also known as hertz, so you can say that's 5.996 times 10 to the 14th per second, or 5.996 times 10 to the 14th hertz. That would be the frequency of the light. Okay? All right. So let's see what let's try to relate this to the real world. What does wavelength and frequency mean? Well, it turns out that wavelength and frequency is associated with what we perceive as the color of the light. Okay, so the kind of electromagnetic wave that our eyes perceives as color, okay, is what we call visible light, things that we can see. Okay, have wavelengths in the range of 400 to 800 nanometers. And like I said earlier, a nanometer is 10 to the negative 9 meters. So if you have an electromagnetic radiation or electromagnetic wave that has a wavelength below 400 nanometers or beyond 800 nanometers, you won't see it. Okay, your eyes are not designed to see it. Okay, so it's still there, but you won't see it. You would call that invisible light or invisible radiation. So there's a whole range of possible wavelengths that electromagnetic waves can have, from very, very short to very, very long. The only ones that our eyes can see are anywhere between 400 to 800 nanometers. So 800 nanometers is over here on this, what we call the electromagnetic spectrum, the range of possibilities. And we have 400 nanometers over here. So beyond 800 nanometers are radiation that you can't see. So immediately after 800 nanometers, you have wavelengths that are classified as infrared radiation. Beyond that, you have your microwave radiation. And even longer wavelengths, you have radio waves. Okay, so if you want to get an estimate for a ballpark figure for the typical radio wave you might encounter, let's say if you listen to 102.5 FM, that's FM is given in megahertz. Okay, so that's the frequency. You can convert that to wavelength if you want. Lambda is equal to C over nu. Okay, mega means 10 to the 6, right? So you can calculate the wavelength of a radio wave. And you could compare that with 400 and 800 nanometers. You can see that that's a very long wavelength. On the other side of the spectrum, you have just beyond the violet end, you might say ultraviolet and then X-rays. Notice that the colors of the rainbow, okay, is related to the wavelengths. The sequence of the colors of the rainbow is actually related to the wavelength of what we perceive these wavelengths to be in terms of color. Okay, so for example, the red end, the 800 nanometer end, is the red end of your visible spectrum, and then the violet end is on the 400 nanometer end. And just remember Roy G. Biv in reverse. Okay, so Roy, red, orange, yellow, green, blue, violet. So the violet end of the spectrum is 400 nanometers. The red end is 800 nanometers. Okay, so anything shorter than violet would be less than 400 nanometers. So this goes down to about 100 nanometers for the ultraviolet, and below 100 nanometers you have your X-rays. There's a bunch of websites that I pulled up here that gives you, let me see, that deal with electromagnetic radiation and how they're related to wavelengths. The color that you see is related to wavelength. I think this one right here might be a nice one here. So you can see on the red end, right here, Roy G. Bibb, green, blue, violet. So the red end of your spectrum, that's going to be the 800 nanometer end, and the nanometers, and the violet end would be the 400 nanometers. So you can see the wavelengths are longer on this end, the wavelengths are shorter on that end. Okay, and here's how light can get separated into its component wavelengths. Okay, so you can see the red, okay, electromagnetic wave has a much longer wavelength than the violet one. You can see this one right here, the crest to crest distance is a lot shorter. Okay, and so if you get, those are the colors of the rainbows. Okay, so these are some nice basic websites for kids that deal with this topic. Okay. All right. So, like I said, since lambda, the relationship between wavelength and frequency is lambda nu equals c, so you can also say that nu is equal to c over lambda. And so the longer the wavelength, the bigger the value for this denominator, the lower the frequency. Okay, so longer wavelength going that way, and lower frequency going that way. Let's do a quick check of your understanding. All right, which color of light would correspond to longer wavelength? Is it red or blue? Turn on the mic. Okay. The long wavelength N is red, correct. Okay. Oops. Maybe I should use a red pen there. So the red, and then that would be the long wavelength N, and the short wavelength N would be in the blue and violet region. What color of light corresponds to higher frequency, red or blue? Okay, I think your mic's kind of loud. Everybody said blue? Okay. All right. Which type of electromagnetic radiation corresponds to longer wavelength, microwave or X-ray? Longer wavelength, microwave or X-ray? Microwave, very good. Okay? All right. Okay, let me turn you off because I can barely hear myself. Sorry. Just type if you need to communicate. All right. So the wavelength and the frequency of a wave is related to what we perceive as the color of the light. What about the amplitude, the strength of the electric field? Okay, that's the maximum possible value for the amplitude. That's the strength of the electric field at the crests. That's called the amplitude, and we're representing that with the symbol E naught in this figure right here. It's related to what we perceive as the brightness of the light, if you would just want to do it in layman's terms. Okay, to be more precise, it's related to what is called the intensity of the radiation. Okay, remember we said a wave is a way of transporting energy from one place to another. So intensity is defined as the energy that's delivered per unit time, per unit area. Okay, so if you have, let's say, a 1 square meter area, and you have light passing through it, and you measure the intensity, the energy that's delivered by the light to that area, that passes through that area in 1 second, that's called the intensity. So if you have more energy being delivered, you have a more intense radiation. Okay, so the intensity, which I'm representing it here by the symbol S, is related to that amplitude. It's directly proportional to the square of the amplitude. Okay, so E naught squared is the square of the amplitude. And the proportionality constant is given by 1/2 times epsilon naught. Okay, this epsilon naught right here is called the permittivity of vacuum. It's a constant, 8.854 times 10 to the negative 12 coulomb squared per Newton per square meter. Okay, and C over here is the speed of light. Okay, and let's take a close look at the unit for intensity. Remember, we said intensity is energy so that's joules, delivered per unit time, so per second, per unit area, so per square meter. So that's the unit for intensity. Okay, so you can say joules per second per square meter. Now a joule per second, okay, energy per unit time is also known as a watt. So that's a watt per square meter. Okay, so just to relate this to something you're probably familiar with, if you've seen your electric bill, okay, your electric bill is given to you in kilowatt hours, right? You're being charged by the kilowatt hour. It's not kilowatt per hour, it's kilowatt times hour. A kilowatt hour is a kilowatt times hour. So that's kilo is 10 to the third, okay? Watt is joule per second, and an hour is 3,600 seconds. So a kilowatt hour, what the electric company is charging you for, is equivalent to how many joules? That's 3.6 times 10 to the 6 joules, okay? So anyway, what we perceive as the brightness of the light is related to the amplitude of the electromagnetic wave, right? Okay, so here's an example. Let's say you have a 5 milliwatt laser beam, and it has a cross-sectional area of 2 square millimeters. So the area of the beam, so you get this laser beam. Okay, the cross-sectional area right here is 2.0 square millimeters. What is the intensity of the beam? So what's the unit for intensity? What is the definition of intensity? It's energy per unit time per unit area, right? And so we know the area is 2.0 square millimeters. So what's energy per unit time? Okay, the milliwatt is millijoule per second. So that's energy per unit time, right? So this is going to be equal to 5.0. Milliwatt is 10 to the negative 3 watts. So 10 to the negative 3 joules per second. Okay, so this is a milliwatt. Milli means 10 to the negative third. A watt is a joule per second. You divide that by the area, which is 2.0 millimeters squared. So I'm going to change millimeters to 10 to the negative 3 meters and then square it. So that's my intensity. You can see here the value of knowing your SI prefixes, which comes in very handy for these types of calculation without having to do the picket fence conversion. So what do you have here? So this is 5.0 times 10 to the negative third over 2 times 2.0 times 10 to the negative 6. 10 to the negative 3 squared is 10 to the negative 6. And the unit is joule per second per square meter. That's your intensity. Okay? And if you did that calculation, the answer you'll find is 2.5 times 10 to the third watt per square meter. Okay? And from that, you can calculate the amplitude of the electric field wave. How? Okay, so our intensity is 2.5 times 10 to the third watts per square meter. So that's 2,500 joules delivered every second per square meter. And to calculate the amplitude, you have to go back to the formula. S is equal to 1/2 epsilon naught C times E naught squared. So what do I do if I want to solve for E naught? I rearrange my equation, right? I have to isolate E naught on one side. So what do? Divide both sides by 1/2 epsilon naught C. That solves for E naught, right? So E naught squared will will just be S over 1/2 epsilon naught times C, or that's 2S over epsilon naught times C. And if I want to solve for actual value of E naught, I have to take the square root of both sides. So E naught is equal to square root of 2 times the intensity over epsilon naught times C. Now, it's best when you're doing this calculation to plug in all values in SI units, okay? And using the base SI units. So 2 square root of 2. What's our intensity? S. Intensity, we just calculated that earlier. Our intensity is 2.5 times 10 to the third watts per square meter. Watt is a joule per second per square meter, divided by epsilon naught. And the value for epsilon naught is right here, 8.854 times 10 to the negative 12 coulomb squared per Newton per square meter. So 8.854 times 10 to the negative 12 coulomb per Newton, coulomb squared per Newton per square meter. And then speed of light is right here, 2.998 times 10 to the 8 meters per second. So 2.998 times 10 to the 8 meters per second, right there. And if you did that calculation, the answer you'll find would be 1.37 times 10 to the third Newton per coulomb. Okay? You'll notice the unit here is Newton per coulomb. That's a unit of force over a unit of charge. Okay? Amplitude of the electric field is the force that a unit charge would feel at a given location. And you should be able to work out your units to come out to be newtons per coulomb. Let's look that up. Look at that. Joule per second. Okay, here's your unit for the numerator. Joule per second per square meter. And the unit for your denominator is coulomb squared per Newton per square meter times meters per second. Okay? And so if you work this out, you should get an answer of a joule per coulomb. And I'll leave that up to you to work out. All right. So anyway, the notion of light as an electromagnetic wave is referred to as the wave model. And like I said, the problem towards the end of the 19th century was that several experimental phenomena involving interaction of light with atoms and molecules could not be explained by the wave model. And a few of these examples are the black body radiation, the photoelectric effect, and the atomic molecular spectrum. Okay, we'll go into those later, particularly photoelectric effect, atomic and molecular spectra. The solution to this problem, okay, to this problem that they were having, is to imagine, instead of thinking of light as a wave, you can explain these phenomena if you were to imagine that light is instead a stream of particles, which means the idea really here is that to think of the energy of light as only available in little tiny bundles. Okay, each of these bundles you can think of as a particle, and so each of these particles we now refer to as a photon. Okay, so instead of thinking of light as a wave, okay, you can think of light as delivering the energy in bundles or packets called photons. Okay, and we can explain this phenomena if we think that of the energy of each photon as being directly proportional to what we would call the frequency of the light if it were if we were describing it as a wave. So it's the energy of the photon is related to what we consider as the frequency of the wave for the light. Okay, and the energy of the photon is directly proportional. The higher the frequency, the higher the energy of each photon. And so this H right here is a proportionality constant, and that's called Planck's constant in honor of Max Planck, who was the first to use that to explain the black body radiation. Okay, so Planck's constant is a universal constant. It's 6.626 times 10 to the negative 34 joules second. The basic idea you have to know here is that the higher the frequency of the light, the more energetic the photons are. So, for example, which has more energetic photons, radio wave or X-rays? Let's see if you remember. Which one has higher frequency, microwave or X-ray? You got it switched. X-rays are down here, right? Microwaves are over here. But this is for wavelength. So X-rays have short wavelength, high frequency. So X-rays have short wavelengths, high frequency, and they have higher photon energies. Lower photon energies here. Okay, so X-rays would have more energetic photons than microwaves. Oh, let me see. Let me try another example, another question. Which one has more energetic photons, red light or blue light? Which one has a higher photon energy? Blue, very good. Because blue on your spectrum, red is on the long wavelength end, right? And blue is on the short wavelength, and violet is on the short wavelength end. So blue light would have higher photon energies. Good. All right, let's just apply this formula right here for the photon energy. E equals h times frequency. Let's say you have red light. Okay, you have radiation with a wavelength of 632 nanometers. If it hits your eye, you're going to perceive it as red light. Let's calculate the energy of the photon of red light. And you just say E equals h times the frequency, and h is 6.626 times 10 to the negative 34 joules times second. Not joule per second, it's joules times seconds. And the frequency is, okay, I'm running out of room here, so 632. Okay, and like I said, you have to put it in meters. So what's a nanometer again? 1 nanometer is 10 to the negative 9 meters. So 632 times 10 to the negative 9 meters. Oops, sorry, wrong. That's wavelength, that's not frequency. Okay, I need to know the frequency, right? So what is the frequency? If you remember, lambda nu is equal to c, right? So if I want to solve for the frequency, it's c over lambda. So c is 2.998 times 10 to the 8 meters per second over lambda, which is 632 times 10 to the negative 9 meters. Okay, so that's my frequency. So I just plug in this number over here. In other words, what we're saying is, the photon energy, which is equal to h nu, is also equal to h times nu, which is c over lambda. So if you plug in those numbers right there, you should get an answer of 3.14 times 10 to the negative 19. I have the answer right here. Let's verify that. 2.998 times 10 to the 8 divided by, let me reset this. Okay, h first. Okay, I need the value of h first. hc over lambda, right? So h is 6.626 times 10 to the negative 34 times the speed of light, which is 2.998 times 10 to the 8th, divided by 632 times 10 to the negative 9. And that should give me 3.14 times 10 to the negative 19 joules. Okay? You'll notice that in joules, okay, this is a very small number, 10 to the negative 19 joules. That's for one, but that's just for one photon. Okay? So that's a very small number. So whenever we're dealing with energies of photons, it's more convenient to define a smaller unit so that we don't have to keep writing this extra power of 10 right here. Okay, so a more convenient unit to use is the electron volt. Okay, skip that one. So typical photon energies are very small, as you've seen earlier. Okay, so like 3.14 times 10 to the negative 19 joules for a 632 nanometer photon. That's the example we just had earlier. You can express that in a smaller unit called electron volt. Electron volt is 1.602 times 10 to the negative 19 joules. If this number looks familiar to you, that's because 1.602 times 10 to the negative 19 is the charge of an electron in coulomb, right? One electron is a charge of 1.6 times 10 to the negative 19 coulomb. So the justification for this name is that if you were to accelerate an electron, okay, through a potential difference of 1 volt. So if you go from one location to another where there's a 1 volt difference, the electron is going to accelerate, okay, by the acceleration is just given by the charge of the electron times the voltage. So the electron is going to accelerate, and it's going to gain an energy equal to 1.6 times 10 to the negative 19 coulomb times volt. 1 coulomb times volt, okay, is a joule. Okay, so an electron that is going to accelerate through a potential difference of 1 joule would be 1.6 times 10 to the negative 19 coulomb volt, and so you call that 1 electron volt. Okay, so a coulomb volt is a joule. So anyway, that's your conversion factor. So let's do this conversion. 3.14 times 10 to the negative 19 joules. Okay. And 1 electron volt is 1.602 times 10 to the negative 19 joules. So that's your conversion factor. 1 electron volt is equivalent to 1.602 times 10 to the negative 19. And if we did that, 3.14 times 10 to the negative 19 divided by 1.602 times 10 to the negative 19. Okay, that should be negative 19 down here. And that should be equal to 1.96 electron volts. So it's a more convenient unit to use for electrons. Okay? Let's go back to this previous slide right here. Okay. Let's say you have in your microwave oven, okay, the frequency of the radiation that's used in your microwave oven is 2.4 gigahertz. And let's say you have a 600-watt oven. You use it for 60 seconds to heat up your water or your soup. Okay, how many photons are generated there? How would you solve this problem? Then you can say, all right, let's first calculate the total energy generated. Okay, remember, anytime you have watts and you multiply that by time, okay, you can get the energy. Remember, a watt is a joule per second, so joule per second times seconds gives you joule. So that will tell you how much total energy is generated by your microwave oven during these 60 seconds. So total energy is 600.0 joule per second, that's a watt, times 60.0 seconds. Oops. So that is equal to how much? 600 times 60 is 36,000. So 3.6 times 10 to the fourth. Okay. 3.60 times 10 to the fourth. And here, per second and second cancel out. So that's just 3.60 times 10 to the fourth. Okay. But the question here is how many photons are generated during this time? Well, the total energy would just be equal to, okay, this is the number of photons times the energy per photon. Okay, so how many photons are generated and how much energy does each photon carry, and how many photons do you have? So this is what we're looking for. This is the question. What's the number of photons that's generated by your microwave oven? So you say N will just be the total energy divided by the energy per photon. Okay? And so what's our total energy? It's 3.6 times 10 to the fourth, right? .60 times 10 to the fourth joules. And the energy for a photon will just be h nu. Okay, what is h nu? So let me rewrite that. 3.60 times 10 to the fourth joules divided by h nu. H, so this h nu right here is h is 6.626 times 10 to the negative 34 joule times seconds. Our frequency is 2.45 gigahertz. Okay, the prefix giga means 10 to the 9. Okay, so that is 2.45 times 10 to the 9 hertz, and a hertz is, so a gigahertz is 10 to the 9 per second. Okay, a hertz is per second, so 2.45 times 10 to the 9 per second. So if we did that, let's plug that into our calculator. We have 36,000 divided by Planck's constant, which is 6.626 times 10 to the negative 34, and divide that by the frequency, which is 2.45 times 10 to the 9, and that gives you this big number right here. Okay, I should be able to write in scientific notation. It's 2.22 times 10 to the something, right? And I did that calculation earlier. It's 2.22 times 10 to the 28. To 3 significant digits, it's 2.22 times 10 to the 28 joules. So that's a lot of photons, okay? In fact, it's more than a mole of photons. A mole is, if you remember, is 6.02 times 10 to the 23rd, right? So that's 2.22 times 10 to the 28. That's not joules. That should just be a number. Okay, make that correction. Photons. Okay, and 10 to the 28. If you divide that by 6.02 times 10 to the 23rd photons per mole, that gives you how much? Divide that by 6.02 times 10 to the 23rd. That gives you 33.68 times 10 to the 4th. Okay? So 36,800 moles of photons. So if you want to count it by mole, you can do it that way. A mole of photon, by the way, is known as an Einstein. So that will be 3.68 times 10 to the fourth Einsteins. Okay, so let's just do a little review of what we've covered so far. Illustrated below is a snapshot of an electric field, of the electric field component of an electromagnetic wave. Did I resume my recording? Yeah, I did. Okay. As it travels through space, at which of the locations indicated would a charged particle experience the strongest force? Is it going to be at point A, point B, point C, or point D? That would be the answer. Okay, can't seem to hear anything. A, very good. Okay, this is the largest absolute value for the electric field. Okay, you are at the trough. At the troughs and at the crest, you have the strongest force. Okay. What's the frequency of electromagnetic wave with a wavelength of 250 nanometers? I'll just leave this up for your homework. What formula would we use here? If you want frequency, then you'll have to use frequency is C over lambda. Okay. So that should be a straightforward plug and chug type thing. You just have to plug in the right numbers. Let's take a look at this one. Which of the following regions of the electromagnetic spectrum has the most energetic photons? Is it X-rays, visible, microwave, or radio wave? Did you answer already? Or okay, X-rays, very good. Okay, so they have the most energetic photons. So if you were on the Starship Enterprise and you were going to fire at the Klingons with your photon torpedo, all right, what kind of photon would be more, what kind of wavelength would you prefer to use? Short wavelength or long wavelength? If you have a choice between X-ray and a radio wave, what would you send out to the Klingons? Okay. C, that would be sending them radio waves. That would be like sending them a radio station. So you want more energetic photons. Okay, so X-rays, if you've heard of X-rays being not safe for you, right? You don't want to be exposed to too much X-rays because the X-rays, the photons of X-rays are so energetic they can actually knock out electrons from the atoms in your body, and so it can ruin your DNA, for example, and cause damage. Okay. Whereas radio waves are relatively safe. You're bathed in radio waves every day, pretty much. You got microwaves from your cell phones and radio waves from radio stations around you. Okay. Let's take a look at this one. Which of the following characteristics of electromagnetic radiation is not associated with what we perceive as the color of the light? Very good. Okay. Wavelength or frequency are associated with what we perceive as the color of the light, and photon energy is just proportional to the frequency. Okay. And this is just another calculation, so you can skip that one. You can do that when you have a little bit more time to actually work on it. Okay, so that's light. The two um, models for light: light as a wave, light as photons. Let's talk about what led to the notion of light. One of the things that led to the notion of light as photons. So here's an example of one of those anomalous phenomena that led to the notion that light is the energy from light is available only in packets called photons. Okay, this is known as a photoelectric effect. The idea behind the photoelectric effect is this: the phenomenon itself involves light being you're shining light on a piece of metal. So here you have your metal right here, and here's your light. Okay, if you shine light on a piece of metal, you can get electrons to get ejected from the metal. Depending on the material, there's a threshold frequency. That means there's a minimum frequency that you need for electrons to be ejected. If you don't have the right frequency, if it's not that, it's below that minimum frequency, then you can't get any electrons off from your piece of metal. And it depends on what the metal is. So different metals have different threshold frequencies. What was the anomalous observation in this experiment? The anomalous observation is that the maximum kinetic energy of the electrons that's ejected does not depend on the intensity, okay? Which is kind of odd, because what did we learn about intensity? Intensity is the amount of energy that light is transporting, right? So you would expect that the more intense your radiation is, the more intense the light, you get more you get electrons with even more energy. In fact, if you don't have the right frequency, if you're below the threshold frequency, regardless of how intense the radiation is, you can't get any electron off. Okay, it actually depends on the frequency, not the intensity. Okay, so remember, the intensity was our measure of the energy of the light, the energy that's transported by the light in the wave model. So it is the frequency that affects how much energy the electrons have. So the kinetic energy of the electrons that are ejected depend on the frequency of the radiation. So that's what led to the suggestion that that light comes only in bundles of energy. So each bundle of energy, if it's got enough photon energy, if it's got enough energy, it can cause the electrons to eject. But if it doesn't have enough photon energy, then it will just the photon will just bounce off your surface, and you're not going to get any electrons. Okay, so that's a phenomenon that led to the notion of light energy being available only in bundles of photons. So this was Einstein's explanation for the photoelectric effect. He said, instead of thinking of light as a wave, think of it as a stream of photons, and each photon carries an energy equal to h nu, as we talked about earlier. So h nu is the energy of each photon. And so Einstein said, for each particular surface material, for each particular material surface, there's a minimum energy that you need to dislodge an electron from the surface. So I've got an electron right here. If I want that electron to get knocked out of the surface, I must provide a photon that has at least that minimum energy phi. Okay? So the phi here is the minimum energy that you need. Think of it as that's the cost of the what's a good analogy here? Think of it as the exit fee for the electron to get out. Okay, so let's say phi is, let's just use a simple money analogy. Let's say it costs $10 for an electron to get out. Okay, then the photon must be worth at least $10. If the photon is only worth $8, then the electron can't get out. Okay, so if your photon energy is less than phi, then the photon can't do anything. It can't get the electron out. But the photon energy is higher than, if it is higher than phi, okay, then it will have enough energy to dislodge the electron. And the kinetic energy of the resulting photoelectron is called a photoelectron because it's an electron that's ejected as a result of a photon hitting it. The kinetic energy will just be the energy of the photon minus the energy that was needed to just pry it out of the surface. Okay, so h nu minus phi. So let's say the photon is worth $15 and it takes $10 to get the electron out. So the electron will have $5 pocket money after that. Okay, so think of electron as being in jail, and the exit fee out of that jail is $10. So if your photon has $15, then it's got enough energy to free the electron, and when the electron is freed, okay, 15 minus 10 would be $5, so that's an extra energy that the electron gets to carry with it, okay? And so where does intensity come into the picture here in terms of the explanation and of the phenomena? The intensity simply means that you have more photons, okay? So the higher the intensity would mean that you'll just be able to eject more electrons. So this would cause more electrons to be ejected, okay, if each photon has, provided each photon has enough energy. So this is like, another analogy I like to use for this is this. If you were to have a high energy photon, it's like firing a bullet to a wall. You can get a chip off the wall because that bullet has a very high energy. But whereas if you have a low energy photon, it would be like firing a million ping pong balls at the wall. You're not going to get any chip off the wall because your ping pong balls, you're just throwing the ping pong balls at the wall. You can throw a million of those ping pong balls at the wall. None of those ping pong balls will have enough energy to knock a chip off the wall. Okay? So here's an example. Let's say you have a 300 nanometer radiation. If you calculate the photon energy for this, how do you calculate photon energy? It's h nu or hc over lambda. So we know our h and c, we know our lambda. You can calculate that photon energy, and you should be able to verify for yourself that that photon energy is 4.134 electron volts. Now the work function phi, this is the minimum energy you need to remove an electron from the surface. In the case of aluminum, is 4.08 electron volts. So let's say you have a piece of aluminum metal and you were to shine light on it with a photon energy of 4.134 electron volts. You need 4.08 electron volts to free the electron from the surface. That's what work function means. Okay? What will happen? Will the electron be able to get out or not? It will be able to get out because, okay, 4.134 is enough to free it from the surface, right? 4.134 minus 4.08, that gives it 0.05 electron volts. So the electron will be ejected, okay? You can eject an electron, and the electron is going to carry with it 0.05 electron volts of kinetic energy, all right? But if your radiation is less energetic, then it might not get the electrons free from the metal.